Okay, yeah, I guess we'll just get started. Like it's about the time, and I'm going to extend a little bit like what we talked about last time. We talked about frequency, right? A little bit resampling stuff, like basically downsampling. So a little bit recap. Then we will talk about some new material. So before that, some announcement or like logistic thing. So I checked the was 1.ou whatever the website. So I think we have like 8 of you guys are registered as a graduate students or like graduate credit hour, and the fellow in Tulsa also is registered as a graduate course here. So, and if you check the course website for you guys, supposed to do some presentation, not some just one, and this is like a tentative schedule for you guys. Like I didn't, I didn't pick the exact schedule for each of the speaker yet, so it will be determined next time. I guess like next Tuesday, but just kind of like want to let you know ahead that that's about the time you will give the presentation. And I'm also like I tentatively I would like you guys to submit a. Let me just get a pointer pen. So difficult. Pointer pen. So just like prepare a title and abstract. I know it's a little bit early, like for those guys, maybe like really far away, but I want you to think a bit earlier ahead. At least give me a tentative title, so I know you already get started. So for the presentation, what's the difference of this from your final project? Is that like the final project, I expect you guys to get actually get things done. So here you can just talk about stuff. For example, like you look into a paper, you didn't exactly present that, but you find it really interesting, you like to discuss that and explain what's going on and so forth. And here also I would like you guys to, okay, I don't know, nice music. So to present something like a little bit more not too outdated, like more recent, maybe like within the last decade. So for the project, like I think it's okay if you work on something that's a little bit dated. For example, like you can work on like license plate recognition, let's say, that I would say technology-wise is actually pretty dated already. Like it's already commercialized, already out there for many years. But it's okay you derive your own solution and so on. You actually put your kind of effort there, like write some code and make it work. But here I really like to talk a little bit more some recent stuff. So, and that's the plan for the graduate fellows, or like anyone who took the graduate credits. So we show some like frequency and some image scaling last time. Basically, this is just a basic recap. So when we have like downsampling, subsampling, then we know that like we have to do a little bit filtering before the subsampling. Otherwise, we may have aliasing like this figure here. This picture here. And this is another example we illustrated last time, that if we don't do kind of downsampling in the right way, we may have like pretty bad aliasing right here. And we talked quite a bit about that, so I will just jump through that quickly. And this is another illustration that like what exactly happened. I didn't have this slide. I think this is a good slide here. So if you do good sampling like this one, after sampling you still have this kind of chessboard pattern, right? Kind of like grid pattern, like every white pixel you have every black pixel next by. But if you do a kind of back sampling like this one, the entire image will become black. So as you see, sampling here. So then the final image will be totally black. Or like you sample like this one, shift it a little bit, it's not as bad as this one, but still like you have a black and then white, and then maybe more white, and then finally have some black and so on. So this is a problem if you don't do filtering and then you do sampling without, when your frequency is not, sampling frequency is not high enough. Okay, and so we talk about, okay, I'll just skip through that. So now this is what we quickly just recap, like what we talk about is downsampling. Now we talk about upsampling. So that is the opposite, right? We have an image, kind of tiny, so we want to make it big. And let's say you have this really tiny image. I'm not sure you can see what is it. I doubt you can. And we want to make it 10 times bigger, let's say. And then the simplest approach will just say for each of them, we just each pixel, you just boost it up like 10 times bigger, right? Like each pixel become like a 10 by 10 with that same color. And this is kind of a Lewis label, like interpolation. And of course, it's not that good. This is the result. As you can see, it's pretty pixelated. So what we want to do instead is we would like to have, okay, actually what we want to do is, I'll just get some opinions for you guys. Like, what do you think, if I give you a problem like that, like to generate a good bigger image, 10 times bigger image, what you think you're supposed to do? Again, for some of you guys already taken signal processing or DSP, that should be, you should try to utilize the knowledge there. Like when you have a signal that is like kind of like a lower frequency, or like it's a discrete signal, you want to kind of expand that. Like how do you kind of like make a kind of you want to upsample that? Like what's the right way to do upsampling? I'm sure like in DSP they will talk about upsampling also. Do you remember like any guys who have taken like DSP? Or like if even you haven't taken DSP, what do you think like a least order improvement compared to this Lewis label?
I don't think upsampling would help. It can make the image size bigger, but
yes, that's a solution. That's upsampling. Yeah, let me address your first concern. Like upsampling. I mean, like if you do pure upsampling like this, I would say like I guess what you are referring to is that you won't get something really amazing. Maybe that's what you're talking about. But it will be better than this one. So and what he just talked about, maybe we can do some filtering for that. It will get a little bit better. And I agree with you also, like, yeah, if we can do some super resolution stuff, but we may talk about that later on. But just in terms of like trying to make it bigger, in terms of like pure signal processing, doing like upsampling, then yeah, a white approach or like the standard approach would be doing some filtering, or like you can think of that way. If I have signal like that, I want to fill the intermediate gap way. So what I showed earlier will be like, let's say I just expand the signal 2 times as big. So the zero order approximation that I show you will be simply having, let's say, like this way. And as you can see, it's kind of pixelated, right? So the least order approximation, obviously, even you haven't studied any DSP, but just to be intuitive, you will just try to do an interpolation between that, right? For example, I mean, instead of like just take this one as exactly copy this guy, I can just interpolate this one like as like the average of these two, right? The labeling two, and this one will be just take these two, and then take this the average of these two and average of these two, and so on to get this one. So right, very logical. This will be like first order approximation. And if you do that, okay, this is more than first order approximation, but I'll show you like first order approximation like this. Then if you do that, in fact, it's actually the same as you're doing a filtering with this kind of triangular filter, basically. And or you can think of convolution with this triangular filter. And let me just jump into that. And basically the resulting interpolation we'll call a bilinear interpolation, just because bilinear in the sense that because we have actual images, say 2Ds, right? So I just showed a 1D example there. So in 2D example, like you first take the average of this. Let's say I just put some number here, 1, 3, 4, 5, something like that. So 6. So if I want to increase the kind of like the image size on both x and y axes, both horizontal and vertically, then let's just put in more number, 5, 6, 7, let's say. So then I will just interpolate this guy as the average of these two, right? So I have 1.5 here, and these two, this guy as average of these two, I have 4.5, and then this point as average of these two will be like 3, and this point average of these two will be like 3 also, and then this point is kind of like average of both. Actually, okay, I should go. Okay. And then this point, let's say, will be the average of these two. So will be what? Let's see, 1.5, 4.5. What's the average of these two? 3.75, something like that, I guess. Yeah, maybe. So and of course I have a conflicting situation here. I can also take average of these two here, so I will get actually 4.5, right? So to deal with that, I will simply take average of these two guys. Then I will have another number, something like that. So basically it's just average of everything, labeling guys. Then I will have a bilinear interpolation. Wow, this is ugly. Let me go back to some other slides. So that's the. In 1D case, it's just a linear interpolation, as I mentioned. It's just a triangular filter. So if I did the Lewis labels, as we show in the first, the worst interpolation would be just like doing a filter with a kind of a rectangular, or like how do we call that? I forgot. How do we call that? Step function, right? And then you can go other shape. Let's say you can do a Gaussian filter and do interpolation like that also. And for ideal reconstruction, we say ideal is like theoretically it's ideal. We'll use the same function. And basically, if you remember last time why we have a same function, is that then we may go back to some DSP perspective. As you remember last time, if we have, if you look at in the frequency domain, we have some sample in frequency. Okay, this figure is a little bit complicated, but so let's say this is the frequency domain of this guy here. So if I sample more, or in the sense if I shouldn't say sample more. If I just extend the signal like this one, so if I insert 0 here, what's going to happen? will have a signal like this. So, okay, this is like in the frequency in terms of like this axis in terms of f. This is in terms of the angular frequency. Oh, where is that? Yeah, in terms of the angular frequency, this should be omega here, right? Okay, anyway. And then in terms of omega, like, then the shape of the signal is like up to 2 pi and so on. Like, the 2 pi is the highest frequency, basically. So if you insert more zeros here, the effect of inserting zeros will be just like, if you remember in DSP, it would be like you have this thing kind of like the whole thing just move towards here. So you can think of like, oh, okay, or I should say like this go 2 pi, right? That's another one. Let's say this is minus 4 pi here. The whole thing will shrink back into scale, like this will go to 2 pi. So, and this go to pi, let's say. So therefore, I have the whole frequency domain is like this. But the parts here, like these guys here, actually are aliasing effect again. So this is the stuff we don't want. So to remove that, like we can apply a filter, right? We apply an ideal low-pass filter will be like that. And the ideal low-pass filter in temporal domain will be like a same function, right? So if I have an ideal low-pass filter to get rid of this guy here, so then in the same effect in temporal domain will be like applying a same filter, doing a convolution with that guy. So anyway, don't worry about that. I added that just for you guys who have taken DSP. Then I guess it's a kind of reminder of what you learned there, that this is a direct application of what you learned previously. So, and we mentioned some of these filters, and bilinear is quite popular doing interpolation, but actually even more popular is something called bicubic. I won't go into that. The shape is kind of complicated. I can't remember it myself. I need to pick it up, or like I'll just call the function, basically. So, but it's like you have a filter, it's basically this shape. And this is just an illustration of the result. Like if I have zero order, like Lewis label, as you see, like really, we showed earlier, like really pixelated, really bad. So bilinear is like this, it's much better, you see. And if you go for bicubic, it's kind of really, I mean, it looks nice, even though it's not sharp, basically. So at least like, it doesn't look like kind of like any artifact. It's just, it's basically the image. Yeah?
So, are there any rules, problems of to what filter to apply if we wanted to do some sort of analytics on, like, image recognition type analytics? Where the resolution is not that good, and we wanted to find out what filter is going to help us.
Actually, this is kind of for aesthetic, or like what was that? Just for I guess like in terms of recognition, if you think of like machine learning and so on, this kind of pre-processing usually doesn't help that much. You can really even get rid of that. Like if you are doing some denoising, maybe that's kind of okay. But if in terms of like just trying to, for example, make it bigger or like smoothing that out, it typically doesn't help. So if you look at like people doing, for example, like using deep learning to do recognition, like image labs, they have really tiny images. They just use that tiny images and they don't try to make super resolution and so on. I don't know whether people try that. I guess because at least in the literature, no one really mentioned. So I assume like most likely someone tried that, it didn't work out well. So
What are the use cases of
this basically is just like you have a TV, you want to look better or something like that. Really only for human. Like, it looks better this way. For example, you have an image, really want to make it bigger, and I guess like for super resolution will be like different stories. Super resolution that like you can, in theory, you can get better, but I still need to hold back a little bit because if you have super resolution but just one image, tiny image, and you want to make it bigger, and you want to make it, for example, you take an image of a license plate, and you try to make it bigger, and then try to recognize that digits inside the license plate. I mean, if you only have one picture, I really doubt that it really help. But what scenario it will help will be you will have actually more than one image. For example, if you have a video camera that's shooting that car is moving away, then in the sense that you have many tiny images, then actually you can take advantage of doing some Bayesian stuff to kind of combine the several images together to do a super resolution that is a little bit better. Actually, I did have a code just for fun, I've written many years ago, and kind of put in on MATLAB. What's that called? This. I forgot how do they call it, the share place. That's one of the most popular stuff that I have as an open source stuff. But many people ask me how did I do that? But the problem is I did that really not something new stuff. Therefore, I didn't write any paper on that, and I didn't bother to write something to explain how it was there. Anyway, it's tracking too far away. But anyway, so you can do something like that basically. If you have many images and so on. Then maybe we can talk about super resolution in the future. But let's see. That's basically we're showing that, right? If you do pure upsampling and do a filtering, that's exactly the same as you doing the convolution with that image count. So and we can do resampling. Actually, that's the I guess is the title of the slides here. So if you want to do resampling, basically, for example, you have this image and we sample to this size here, then the standard way will be just do a upsampling and then do a downsampling. Then, of course, when you do upsampling, you need to do filtering, right? And downsampling, you need to do filtering again. So therefore, you can merge these two filters together, just make one filter to save your time and so on. So this is some kind of not quick. I guess I just a little bit explanation for resampling, and I guess a little bit extension of what we talked about last time. So what next? I'd like to talk about Gaussian Pyramid. I will have another set of slides for that, but let's see. Okay, I kinda. Okay, so I change my color again. So quickly move to another topic. So we'll talk about image field. It's a bit related to what we talked about just now, but again, you see it's actually again have some upsampling and downsampling, but they do it a different way. So I kind of I shouldn't say copy, but I was inspired by a lecture by this Professor Shark. I guess he's oops, I guess my Suno pen is not working. Let me just, maybe I should restart it. Let's see. Where is it? Where is it? Where is it? Okay, this is working now. So you can find his lecture online, actually. So, and if you don't understand what I'm talking about because of my accent or something, you can also look for his lecture. But he has a different accent also. He has an accent for if you don't like the Chinese accent, you can try the Indian accent, basically. So, he's more or less about this paper here. It's a very well cited paper. It's a bit dated, but still like this kind of used for many applications. So it's interesting to talk about. I guess it's back in the 80s. It's well cited. Like you have like 7,000 so many citations. Of course, this is like last year. Probably now has more citations number. And I also copied this fun slides from him also like that. But actually, who remember that? Like, what's the seven whatever? Like, was like a miracle or like what 7 wonder of the world or something like that? You just showed that like in that slide, but anyone remember like can? Of course, pyramid is there, was there. Of course, the 7 wonders according to in the middle, how do you call that? Like, in terms of like European view, they don't include anything in India and so on. So they have like, I don't know, lighthouse at Alexandria and so on and so forth. Lots of the colossals like Rose Island, but actually only the pyramid left behind basically. They have all these hanging gardens like in Babylon and so on and so forth. So pyramid, so we talk about this image pyramid. Basically, it's something like that. So we have an image. So we just have like smaller scale. Like we just have a what's that? Kind of down sample. You can think of like have a shrink resolution in a lower resolution and lower resolution. So there's lots of applications for that. I would just say talk about 2 applications at the end, but you can think of like applications, for example, if you want to do recognition. So people do multi-resolution recognition. They can first do a Gaussian pyramid and kind of train at different level. And typically you try to maybe like recognize something at this level and then propagate back. And sometimes you can speed up your algorithm and speed up your implementation and so on and so forth. So, and that's another example of another image of Gaussian pyramid. So, and we will also talk about the Laplacian pyramid. It's very much related. So, basically the pyramid, Gaussian pyramid, just composed of these 2 operations here. We call it like reduce and expand. So basically reduce is just like each time you shrink the image into a bit smaller, and then basically you have this reduce operation applied to image many times. Each time you get a new image, basically a lower resolution image, and you keep doing that, and then you form the whole pyramid. And the expand will be just the opposite, right? You have the low resolution image, you expand it, and then get a bit higher, and then expand it again, and so on and so forth. So, I'm actually one reason I talk about that is that the application will appear in your homework too. So of course it's a bit early to talk about that. Like, I didn't set up the due date yet, but yeah, I used to talk about this later. Last time, I mean, in the last year we talked about, for this thing here, but I think like this ordering is a bit better because we just talk about this frequency stuff. It's reasonable to talk about this now. So the reduce operation is like this. Equation-wise, a bit, I don't know, like it's basically like this. So we have this filter here. This is a filter. This is the image in lower level. Basically, the lower level image is is the bigger one. So you just go up, then you get smaller and smaller. So first things first, like you see this equation, what does it remind you for this equation? What does it look like? So a little bit hints that we didn't talk about much. We talk about correlation and convolution, basically. So does it look like more correlation or more like convolution?
Convolution.
Yes. It's actually very similar to convolution. So only thing is that we have a 2 here, you see. Like if we don't have this 2, it's exactly convolution. So with this 2, it's just like we actually did downsampling right away. Or you can think of like, because we are not going to store those things, so we are basically not going to compute that. So this is just an illustration. So basically we are doing a kind of like a filtering like this. Like it's a convolution, but at the same time, like actually on the same time, honestly, this convolution will be the same as correlation, because in practice we will typically use a symmetric filter here. So, but anyway, this is the original how they present it. Just let's stick with that. So and as I said, like basically it's just applying a filter like along the. Okay, this is one. Okay, I should explain this figure first. This is a 1D illustration. Of course, like this is just, you can think of the lowest level image or lowest level signal. Then when you go one level, you just kind of reduce the size by half. So then basically you just remove, or like you just ignore every other sample. Basically, you're not going to compute that, or you can think of you compute that, then you remove that. But since we are not computing that, I mean, since we are not going to store that, so we are not going to compute it anyway. So then we can repeat that like, so in the next level, we just repeat that, and so on and so forth. And it's very simple. And then the expand operation is kind of the opposite. So we have expression like that. Just a remark here, this expression, I can result in indices that will be, let's say, for example, if I have I is equal to 10, let's say n is equal to 0, or I shouldn't say pick 10. Let's say I is equal to 9, n is equal to 0, then I will result in indices, I say 4.5 way. So this is something. So in this case, of course, like basically like the image only have index, basically integer. So in that case, we will just assume like non-integer indices will have like value equal to 0 in this case, rather than doing interpolation. So that's our convention here. So therefore, like if I have, let's say, just give an example, expand this guy here, and let's see, for I, let's say equal to 2 in this case, I just substitute everything here, and then as I mentioned, if the index is not integer, then in that case I just assume that this value does not exist, or like this value will be 0. So this 2 will be gone. So basically I only have like these 3 terms here. And yet another example, let's say I equal to 5, I have basically these several values. I only have 2 terms here basically. And pictorial wise will be more intuitive. I will have something like that, right? So for the even sample, I'll be basically doing filtering, or like do a weighted sum from 3 different samples here from the upper level. And for all indices, I'll be doing like a weighted sum of like 2 samples only. So that is the expand case. So very simple operations. So of course, what I show here only 1D, and 2D will be just expand for both dimensions, right? So it's very simple. So what you can do is first do one dimension and then do the other dimension, basically. And so that's basically the separable property. We will do one dimension and then do the second dimension afterward. We will kind of like also impose a symmetry property. That's in the sense there's no particular reason why why the weights or like the filter should not be symmetric. So we'll just assume this W minus 2 will be just equal to W2, let's say. So therefore, like the filter will be just like having this value, let's say CBA, and then like, and we don't want to change the power, the energy of the signal, so we'll just like have this value added, the sum of all these coefficients added to 1. And also we want the kind of the contribution to be unbiased. So what I mean is like, if you think of like doing the reduced operation, like going up, so all the contribution like from let's see. So if I look at the reduced operation for free labeling kind of like points here, so as you can see, like 1, I get value from this like 0 to 4, and then this 2 is weighted sum from this like 2 to 6, and so on. And now what you can see is that for this pixel 3, I shouldn't say pixel 3, or sample 3. Sample 3 has this contribution like to this guy with this weight B and B, right? But for sample 4, I have contribution like to these 3 guys like CAC, right? So there's no particular reason why like your odd sample like contribute more than the even samples or the other way around. So what we can do is that we also impose a constraint that like the sum of this 2B should be equal to the sum of C plus A plus C. So then we have another function, another equation here. So with all these equations, like this one and this one, then we have some constraints for this A, B, and C. Basically, like only have one freedom. Degree of freedom is B. So let's say we will pick. Oh, sorry, it's not. Actually, from this 2, we'll get like B is equal to 1/4. Then we substitute back, we have this here. So I should say like the only one degree of freedom is A. So if we define A, then everything is fixed. So then the design parameter here typically is like either you pick A is equal to 0.4, then you have the filter is kind of like similar to a Gaussian shape, kind of like model a Gaussian shape. If you pick 0.5, you have kind of like triangular. So, wow. Okay, I go pretty fast today. So I guess it's okay. Let's see. So now for the Laplacian, then basically the Gaussian pyramid, as you can see, we just keep doing the reduce, right? You do reduce, and then you have the Gaussian pyramid. And for the Laplacian pyramid, it's just a kind of slight modification. Basically, you first construct Gaussian pyramid, and then afterward, your Laplacian pyramid will be just the difference between like two adjacent Gaussian pyramid. Of course, they have different size, so therefore, like I shouldn't say adjacent pyramid, but adjacent level of the pyramid. So then, but the two levels will have different size, right? So therefore, I should expand one of the level. For example, like for the L0, basically, I'll expand the next level, like G1, to make it the same size as G0. Then I take the difference, I will get the Laplacian pyramid for that level. So this is an illustration for that. So this is the original image. If I keep doing the Gaussian pyramid, I have this way. So this should be different sizes. So then I do the Laplacian pyramid, get the first level, will be basically expand the next level of this Gaussian pyramid. This should have same size of this guy. Then I subtract it, I have this guy here. So you have something, because you look at the Gaussian pyramid, they all look pretty similar, right? So when you expand this guy, you have a difference. It's kind of like almost an edge detector here, or like you only have the residual is like almost all zeros, and you keep doing that like for other other levels, this is a little bit not the ideal illustration here, because I want to emphasize again, like the sizes, like for these guys should be, each of them is like getting half of the original. So this should be half of the size of this guy here, and this is a quarter of size of the original. This is a 1/8 of the size of the original. And similarly, also the same for this Laplacian pyramid level as well. So then immediately one application you can see is that I can do compression, right? Because for the Laplacian pyramid, if I have the entire Laplacian pyramid, then I can reconstruct the original image. And at the same time, the Laplacian pyramid, like most of the coefficients are zero, therefore I can just throw them away. So therefore, a kind of like a very simple application would be just for like compression, and I'll illustrate that like I'll show that like in the later slide. But this is just a kind of summary again. Like where is that? This is not. This is exactly the image compression basically. So encoding, I found the Gaussian pyramid, and then use the Gaussian pyramid to construct the Laplacian pyramid, and I need to be careful. For the Gaussian Laplacian pyramid, for the last level, we will simply take the level of the Gaussian pyramid, and then as I said, like for compression, we'll simply quantize these values here. So we quantize that. That basically means that we'll essentially throw away some of the zeros and like small values, and then just do Huffman coding to further compress that. And that's some illustration that we have different levels, and then we quantize it, I think this is the okay. This should be the yeah. Okay, this should read this way. I think like this is the first Laplacian level, the second Laplacian level, the third Laplacian level, and then like after quantization of Huffman coding, like the first level, I have the number of per sample. The number of bits is a 3.36 maybe. And then this is a 1.99 and so on and so forth. And so decoding is just going backward, right? So it's very simple. So the last Laplacian pyramid is basically exactly the same as the last Gaussian pyramid, I mean the level. So, and then the rest will be just doing the opposite step. So we expand the Gaussian pyramid in the lower level and then add it back to the current Laplacian pyramid level and construct all the Gaussian pyramid level. And by the way, what is the original image? Anyone is still listening? So yeah. So what's the original image? So after this step, like reconstruction, where's the original image? Yes? What? Yes, G0 is the original image, right? So, yeah. Oh, is that G3? Oh, okay, anyway. Yeah. Okay. So, anyway. So, yeah, you go all the way back, like G0 will be original. So, for that, the convention is that, like, you have, whatever G0 or something is the original image, and then you shrink when you go up one level. So, and So therefore, like after all this step, like you get to reconstruct the image with G0. And this is a compression result. Of course, like this is very old work, like basically 80 something. So it's not impressive at all, but it's just like one simple application. So instead, like I like to do like one interesting application of this, like very simple application, is do an image blending. So you call composting also. So you have, for example, an apple, image of apple, image of orange. You just fuse them together. So it's very simple to do. Basically, again, I construct like the Laplacian pyramid for, let's say, the orange image and then the apple image. Then you just pick half of that, like from one image, half of that for another image for each of the pyramid. Each level of the pyramid, and then you do the reconstruction. Then you get this very nice fused image. Yeah. So I can, let's see, I think I have code here. Also, I can show you a quick demo. Let's see. Where is it? So let's say I just use Octave. So Octave is basically the same as MATLAB. So if you don't want to bother to kind of like install MATLAB, especially with the license issues. I know, like I don't know for you guys. We can use MATLAB at least as faculty member, but we need to stick with the license. What do we call it? License the manager or something like that. Yeah, that they once you get offline, then you cannot use it. So it's kind of bothering. So so sometimes when it's possible, I will just use Octave. Therefore, and let's see. I think it's this one. It's something like that. So it doesn't look good, but this one only have 2 levels. So I decompose into 2 levels and I merge together. So if I have more levels, let's say these 3 levels, a little bit better. 4 levels is even better. I guess I only do up to 4 levels, is that? Oh, I even have 5 levels. So 5 levels look pretty good. So your homework will be like, you just take your friend's photo and your photo and try to merge together. You don't like to merge right up and down or like left and right, is up to you. But just try to merge them together. I didn't set it up yet. I don't know what's the due date, but that's basically it. Wow. Yes?
Didn't you say there was a bonus for using Python instead of MATLAB?
No, actually, I talk about bonus. Bonus is about what's that called? Piazza, like answering questions in Piazza. Yeah, not for that part. But for more complicated homework, this tool is relatively simple. But later on, if I have more complicated homework, I will give bonuses for the first completing guide. So. Of course, need to have correct solution, like more or less correct solution, like 90% correct solution. I will give bonuses for that, just to encourage you guys to complete earlier. For Python, yeah, I have time here, so I have. Let's see what I can do. I have some personal stuff. I shouldn't show it. Let me just close all of this. I closed more than I should supposed to close. Let's see. This is okay. This is for fun, but I shouldn't show it also. This is a kind of interview of Eric Smith with like this Les Freeman, and I just transcript that. Like I use I try software like online to do transcription, but anyway, I shouldn't go that far. Let me just maybe one thing I can talk about, like just quickly, is Oh, I'm not sure how many of you source you mentioned using Python, and I'm not sure how many of you are using Python and Linux already. So and I have no intention to give you bonuses for that yet, but I really highly encourage you guys to like use Linux and Python and stuff like that, because if you use Windows and MATLAB and look for a job, it won't help basically. Especially MATLAB, you go to like small companies. What MATLAB? What is that? No, they know what's MATLAB, but like we don't pay for that. Are you going to pay for it? No. Oh, should I actually recording that? But it's okay, right? I guess it's okay. MATLAB didn't pay money for me. So if you want to pay money for me next time, I'll say good word about for you. But what I mean is like realistically, companies will go for anything inexpensive, right? So Linux is free, and then OpenCV and all these stuffs are free. So I will kind of encourage you guys to look into those. It will take you a little bit time, but when you send out your resume, it really helps. I can really be sure about that when you look for a job. And I just put up a little bit note, thinking when I run into a situation like this, I really have too much time left. I may go for some. So I don't know how many of you how many of you are Linux user? Seriously? Really? Oh, okay. So therefore, I'm not wasting your time, I guess. So it's just like something. I find that I only put in everything here is really essential, because the thing I use day in and day out. So other commands I don't remember. These are commands I remember. So simplest things, right? You need to go, just like Windows, you go into terminal. Okay. For Linux, one thing is that you always go into terminal. It's not always, but if you want to get more out of that, like you like to use a little bit terminal, right? Then you need to get a one with the folder. Then it's just like in Windows, you have the CD, and you CD like ... then you go back to the previous directory or the previous folder. If you CD nothing, then you go to the home folder. This is something like different from Windows, I guess. So also like you have this CD tutor also like, I'm sorry, let me just make it bigger. I'm sure like no one can see it. Yeah. CD tutor is also mean home folder. So go back to your home folder also. So for example, I can put like this is CD Dropbox, like to the Dropbox. So what else? What's the essential stuff? Okay, ls, like if you are from the Windows, ls is mean dir. So you have ls, then you have like list all everything in the folder. So you something I find very convenient is like ltl, something like tl is this will sort your listing kind of like according to time. So this is I just make changes here, for example. So it's very convenient. That way. Also, like you have ls/a or something like that. It's like basically show your hidden folder, and maybe ls/1 this show it as a one list, something like. And if you're using Ubuntu, so I guess many people use Ubuntu. I don't know, like Linux user, like what you're using. Debian, yeah, it's same as Ubuntu. So you use the basically, you use apt for package managing. So actually, for one thing, like I guess Windows is really, I don't know, very at least for Linux user, like after you use it for a while, you really don't like about Windows is like it doesn't have a real package manager. So you go to some website, you download something, and then like you install some virus, and then you try to clean it and stuff like that. So for Linux, most of the time you just you don't go to website to install software. So you have a package manager, or like you have software here, something like that, like you have something similar in Windows 10 maybe. Let's see, software. Yeah. But many times I don't go to here, and you can have like sudo like apt get install something. For example, get install like vim. I probably have vim here already. Oops. Oh yeah. So sudo here is basically like, it's just that you want to run things as administrator. So because I install things into the system, so therefore I need to use sudo. And also, like if you don't know the package name, you can use apt cache search something. Let's say, for example, vim. Then you get lost all the relevant packages. Then you can install whatever. That's about package managing. And one thing is like, okay, okay. One thing also, if you want to get sometimes occasionally when you're really stuck with your GUI, like the Windows system is not, I don't know how frequent for you guys, like when it really happen, or like maybe you need to install some Windows driver, display driver. In that case, you need to get out of the window manager, and then you can, I'm not sure you can still see anything, or you cannot actually. Oh, okay, anyway. Or maybe I won't talk about that. That is a little bit advanced, or like not daily stuff. So, editor, you can use gedit, for example. Like I can use just gedit for editing. Okay, when you have a job or something, like I have gedit something, then if you go back to the terminal here, so it kind of stuck here, right? So you can press Ctrl+C to break whatever you're running. So you will kind of suspend that. So you see that it kind of stop here. And then you can put BG. That means that you're going to put this job into background. So it will go to the background one as a background. If I use the command FG, it will put back to the foreground. So if I press Ctrl+C, it will break it. So and I can use PS. It's like see what kind of job I have, like PS AUX typically I use. So you see like what kind of job, and then for example, like I have grab is like kind of I list everything. I want to grab that particular command here. I just want to see like I have stuff running as VLC here. VLC is the whatever, the video player, right? So I can kill this job with like kill -9, the job number here. Then I'll kill that. What else? And some of the stuff is a little bit I find like is as more relevant to this class is like doing video or like images. FFmpeg is really convenient. So for example, you want to kind of cut videos, like you don't want to use GUI. I typically don't use GUI. Actually, you can, let's say I have a video. Actually, I'm still kind of like recording this video here, let's say. I don't know what video is that. Hopefully it's not something like I shouldn't show. If then I need to cut the video or something. Oh, okay, that's some presentation I try to make. So for example, I can just extract the audio, or I can like just cut the video, like this is I kind of like, this means that like the code I just copy it. And also for the audio code I copy it. The video code I also just copy that. And then I start from some whatever, like start from like maybe 1 minute. And then I, with length like let's say like 4 seconds. And then call it out2, let's say. Then I have an out2, something like that. There's 4 seconds, something like that. Then, what else? And then actually, if you want to, I just show one that may be fun for you. Like, let's say, this command, what it will do is a little bit complicated. It looks like it will basically extract all the audio channel from all the MPEG-4 images in your folder. So this is like some of the stuff I found it really convenient as a Linux user. It's like sometimes in Windows it's really painful to do. Like for example, if I have like folders of like a bunch of just video, I want to extract all the audios here. Like in this case, in Windows, maybe I really need to go find some particular software to do something really crazy, and maybe in the meanwhile, I just install a couple viruses and then I try to kill the viruses and so on. But in Linux, you can just say one-line command, you will do that. So it's really nice. So that's advertisement for Linux. So maybe I should just stop here. And then maybe next time I talk, let's see, when I have more time, I talk a little bit more about like installing OpenCV and so on.